Hello guys, let's consider this problem about waves and oscillations. A small sphere mounted at the end of a vertical rod dips below the surface of shallow water in a tray. The sphere is driven vertically up and down by a motor attached to the rod. The oscillations of the sphere produce traveling waves on the surface of the water. Okay, here the rod is oscillating up and down, producing transverse waves. Part A. The diagram shows how the displacement of the water surface at a particular instant in time varies with distance from the sphere. The period of oscillation of the sphere is 0.027 seconds. It is also the period of the wave. You know, such a picture is named wave profile. In a wave profile, we have freezed the wave, and so displacement of each particle is shown on vertical axis in millimeters, and the distance traveled by the wave is shown on horizontal axis. Of course, you know that the energy transfer will be on horizontal axis. Okay, use the diagram to calculate for the wave, the amplitude, the wavelengths, the frequency, and the speed. Okay, for the amplitude, it's very easy. Suppose that I have a particle like m. M will have its equilibrium position like m prime on horizontal axis, and it has been displaced this peak from m prime. Maximum displacement for m upward or right or downward will be 1 millimeter exactly, not more. So it could be regarded as amplitude. For any other particle, the situation is the same. Any other particle like n will have its equilibrium position like n prime on horizontal axis, and maximum deviation from its equilibrium position will be exactly 1 millimeter up or down. You know that m, n, or any other particle will not move rightward or leftward. They just oscillate up and down. So amplitude of the wave will be amplitude of each particle. So I can write it in SI units as 1 times 10 to negative 3 meters. For the wavelengths, I should find two consecutive similar points like P and Q, like M and N, which are successive and similar. So the wavelengths estimately is about 7 millimeters in my approximation, or 7 times 10 to negative 3 meters. For the frequency, you easily can have the inverse of the period. The period was given to you 0.027 seconds, so the inverse of that value will be 37 hertz. And at last, the speed of the wave will be multiplication of lambda and the frequency. In SI units, I will have 0.26 meters per second. Of course, this is the speed at which we have energy transfer. Part B. The wave moves from region A into a region B of shallower water. The waves move more slowly in region B. The diagram not to scale shows some of the wavefronts in region A. Okay, you know that if I have another ray like this is a ray perpendicular to wavefronts, okay, this ray will bend toward the normal. If it is normal, will bend toward normal in region B. The reason is evident because in region B we have a slower wave, and so deviation will be towards normal. With reference to a wave, distinguish between ray and wavefront. Okay, we know a ray is a line or arrow that shows the direction of propagation of wave or energy transfer. If this is a wave, it could be a ray, an arrow indicating energy transfer. Wavefronts are lines connecting points on the wave that are in phase. It's very important, in phase. They could be on one crest or one trough. So those lines like this, white lines, could be regarded as wavefronts. On each wavefront, you will find too many points which are in phase. You know that the distance between two consecutive similar wavefronts will be lambda. Okay, double I. The angle between the wavefronts and the interface in region A is 60 degrees. This is 60 degrees here. The refractive index from A to B is 1.4. Okay, determine the angle between the wavefronts and the interface in the region B. Okay, let's have normal line, two normal lines like this. Okay, and we know that this ray will make 60 degrees with the normal. The reason is this. In this triangle, you see a 60 degrees here, a 90 degrees here, so it is 30 degrees. If you take 90 degrees here, you will have again 60 degrees. Likewise, this 60 degrees. If I draw another ray parallel to the previous one, it will make the same angle 60 degrees with the normal. This is angle of incidence. It will bend towards the normal, as I told you, because in region B we have slower speed, and so it will make an angle of theta B with the normal again. After that, we will find the angle between wavefronts and the interface. Okay, I will use the general rule for a Snell law for refraction. NA sine of theta A is equal to NB sine of theta B. NA and NB could be simplified, and you can substitute 1.4 instead of NB given here. Theta A is 60 degrees, so sine of theta A could be square root of 3 over 2, and then sine of theta B is something I'm going to find it. Theta B is found to be 38 degrees. Okay, I put 38 degrees here, and I can have some wavefronts, and wavefronts is easily seen that will make the same angle 38 degrees with the interface. You can prove it easily. In III, on the diagram above, construct 3 lines to show position of 3 wavefronts in region B. I draw them. Okay. Part C. Another sphere is dipped into the water. The spheres oscillate in phase. Oscillate in phase. So I have 2 wave sources oscillating in phase. The diagram shows how some lines in region A along which the disturbance of the water surface is minimum. Okay, they are lines of minimum disturbance. Minimum disturbance means destructive interference. Part I. Outline how the regions of minimum disturbance occur on the surface. Okay, it's easily justified by destructive interference. Let's go closer. Here you see, for example, these blue lines. Suppose that this blue line or blue curve is the crest of one of the sources. This is another successive crest. Between 2 successive crests, I will have a trough. This trough is exactly overlapped with the crest of the other one. So a trough and a crest has been overlapped to make destructive interference. This is the reason that on those lines we can have a very low amplitude or minimum disturbance. Okay, double I. The frequency of oscillation of the spheres is increased. State and explain how this will affect the positions of minimum disturbance. Justification is based on lambda. You know, wavelength is equal to V over F. V is constant. The reason is evident. You know, velocity or speed of the wave is a property of the medium. The medium has not been changed, so velocity is constant. If you increase the frequency, the denominator of the fraction is increased, so the whole fraction will decrease, and so lambda will be smaller. For smaller lambda, we have a contraction for the pattern of interference. So the lines of minimum disturbance, the wavelengths, everything will be smaller because the whole pattern will contract. So the position of those minimum disturbance and everything will be closer to each other.